Hello Math 1224, this is Dr. P with Lesson Launch 14.2, Staring into Space. In this video I wanted to take a second look at the series sum from k equals 1 to infinity of a sub k, where a sub k is 1 over k times k plus 1 for all k greater than or equal to 1. That's the same series that we looked at in the last video. So last time, you'll remember, we came up with this conjecture. We came up with the conjecture that if we define S sub n, the nth partial sum, if we define that to be the sum from k equals 1 to n of S sub k, or sorry, not S sub k, the a sub k, so the sum of the first n terms of our series, then S sub n is equal to n over n plus 1 for all n greater than or equal to 1. And if we know that, then we know how to find the sum of this entire series, because as we said in the last video, the sum of this series, if it's defined at all, it's defined to be the limit of this sequence of partial sums. Now, one thing I wanted to do was just kind of give a little intuition for why in the world we even define the sum of a series that way, because I realized the way I presented it in the last video might not have come across as totally natural. So if I write down a few terms of this infinite series and pretend like I'm going to write down the entire series. I don't quite have time to do that in this video. Y'all have complained about them being too long as it is. But if I write down the first few terms, then this is what I get. I get something that looks like this. I'll even write down one more. There we go. So that's what my series looks like. So the whole idea of calculating partial sums is that you sort of pretend that you're adding up a long list of numbers. If you're adding up a long list of numbers, you don't add all of them at once. What you do is you sort of start at the beginning of the list, and then you keep a running tally in your head, or somewhere, maybe on paper. I'll do it on this tablet. So first I have the term 1/2, and then I add 1/6, and then after doing that I get the sum 2/3. And I take 2/3, and I add 1/12, and I get, let's see, that's going to be 3/4. And then if I take 3/4 and add 1/20, then I get 4/5, and so on. So these numbers in green are not numbers I'm adding up. They are the results of adding up some terms of the series. Okay? So the whole idea of this limit of partial sums business is if I keep going like this, then my running totals are going to be numbers like these: 6/7, 7/8, 8/9, and so on. And you just see that those, if you look at them on a number line, from 0 to 1, those partial sums, they're getting gradually closer and closer to 1. They're never going to reach 1 exactly, but the limit of those partial sums is going to converge to 1. Okay, so what's happening is, as I add terms of the series, I'm jumping along the number line like this: jump, jump, and then another jump, and then another jump, and so on. And at this point, they're too small for me to draw well using this pen. But each of those jumps represents me adding some term of the series. And then the idea is that the accumulation of all these jumps is going to take me not quite to 1, but it's going to take me as close to 1 as I want to go. And that's why the limit of this series, or the sum of the series, is 1. But anyway, the point of this video was I wanted to share a way of proving this conjecture, because I actually think this is super cool. If you don't think this is cool, then I just don't know what to do with you. And I haven't shown you yet, so if you don't think it's cool yet, that's okay. But I hope that 5 minutes from now, I will have totally sold you on this. Okay, so anyway, we were given the definition a sub k equals 1 over k times k plus 1. Now I realize I've been switching around which letter I'm using, but that's totally allowed. I'm going to use k to represent indices for individual terms of the series, and then n to index the partial sums, just to keep things separate. Now, look at this expression here. Now, you've encountered expressions like this before. You've encountered them, for example, when we were trying to integrate functions like this. So if this were a 1 over x times x plus 1, and I told you to take the integral, what technique would you think of using? I don't know about you, but I would think of trying to rewrite this using partial fractions. Partial fractions. I'm going to try coming up with a partial fraction decomposition of 1 over k times k plus 1. So if it has one at all, and I think it will, that partial fraction decomposition is going to look like this. A over k plus b over k plus 1. Okay, now at this point I'm going to assume that, rightly or wrongly, that you know how to do the algebra on this, and I'm going to skip over the process of doing the algebra and just jump to the good part, where I find out that a is equal to 1 and b is equal to negative 1, which means that 1 over k, k plus 1, is equal to 1 over k minus 1 over k plus 1. And you can verify for yourself that that works, that that's entirely consistent. Oh, sorry, that was the undo button. I keep getting the tools on this thing mixed up. Anyway, so what's the point of all that? Well, if I am trying to add up terms like 1 over 1 times 2, plus 1 over 2 times 3, plus 1 over 3 times 4, plus 1 over 4 times 5, and so on, well, according to this formula here, that's the same as adding up 1 over 1 minus 1 half, because this is saying that 1 over 1 times 2 is equal to 1 over 1 minus 1 over 2. And then this next term is just the same as 1 half minus 1 third, and then the next term is 1 third minus 1 fourth, and then the next one is 1 fourth minus 1 fifth, and so on. Now suppose I add up. Now technically this is written as 8 terms, but when we're thinking about this series, it's the first 4 terms of the series. So this is really the 4th partial sum of my original series. And I'll bet that you could add that up in your head. There's a lot of terms, but a bunch of them cancel out. Like these cancel out, and these cancel out. These cancel, and I'm left with 1 minus 1 fifth, which is 4 fifths. So in general, S sub n is going to be, well, let's see, that's going to be 1 over 1 minus 1 half, plus 1 half minus 1 third, plus dot, 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 yada, 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 Seinfeld. And then I think that last term, well, since the first term was 1 over 1, and the second term was 1 over 2, I think the nth term is going to be 1 over n minus 1 over n plus 1, according to that formula, that partial fraction thing I came up with earlier. And so, well, what's the sum of all that? Again, I can just go through and slash and burn here. I'm going to come up with a different color, I think. There we go, a nice orange color will do nicely. Cancel, cancel, cancel. There's also a plus 1 third in here, da 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 da. There's going to be a minus 1 over n just before this, and I'm left with 1 over 1 minus 1 over n plus 1. So S of n is equal to 1 minus 1 over n plus 1, which is n over n plus 1. Boom. Proven. Okay, now that's, some people would not accept that as a rigorous mathematical proof, because they would say, well, what kind of reasoning are you hiding between these dot dot dots here? Now, I'm not going to concern myself with that too much. I hope that you found that convincing. I find it a pretty convincing argument. If you wanted to make it more rigorous, we could talk about that. But anyway, that shows that S sub n is equal to n over n plus 1. So going back to my number line diagram from earlier, so what all that means is that on that number line diagram, every time I make one of these jumps, I'm jumping to another term in the sequence n over n plus 1. So this is 1 over 2, this is 2 over 3, not the jump size, but this number here. And then this number here is 3 over 4, 4 fifths, 5 sixths, etc. And my limit of these S sub n's is going to be, the limit as n goes to infinity of n over n plus 1, which is 1. And we did the algebra for that in the last video. So what that means is that the sum of all these sequence terms, that is the sum of all these little jump sizes here, is going to be sum from k equals 1 to infinity of 1 over k, k plus 1. That is indeed equal to 1. Now, by the way, there is a little less formal way of seeing that, using this canceling idea, which is that if I unpack that, then I get, well, 1 over 1 times 2, plus 1 over 2 times 3, plus 1 over 3 times 4, etc. Well, that's 1 over 1 minus 1 over 2, plus 1 over 2 minus 1 over 3, plus 1 over 3 minus 1 over 4, and this just keeps going forever. But as this keeps going forever, what happens? Well, these halves cancel off, and these 1/3s cancel off, and the 1/4s cancel off. If this keeps going, the only thing that doesn't eventually get canceled is 1 over 1. So that's an informal argument that the sum of the series is equal to 1. You just have to be careful with that kind of thing, because sometimes these infinite cancellations, it looks like everything's going to cancel, but in the meantime you've got partial sums that are not converging. That'll usually happen if these fractions values are getting larger. So I just want to be cautious about that. But anyway, the thing that you just saw here is an example of a phenomenon in mathematics that we call, let's see, where's my purple marker? Thing is, this doesn't hold a lot of different colors at once. I have to remake them. This is called a telescoping series. Hence the title of this video, Staring into Space. The telescoping, I'm not quite sure why they call it telescoping, but if I had to guess, I think it's based on those old-timey telescopes where there's like a piece here, and there's a piece here, and then there's a piece here, and then there's like an eyepiece all the way over at this end, but the whole thing collapses. Like this part goes into this part, goes into this part, and so on, so that you just get one of these. So it's like everything in the sequence, or the series that is collapsing. Okay, I think I barely met my promise of being shorter than the last video. Now in the next video, I'm going to talk about why in the world this discussion of series even belongs in this course. What does it have to do with anything else we've done this semester, besides the whole partial fractions bit? That was pretty cool. I don't know, like I said, if you're not a fan of this, then I don't know what to do with you. This is pretty cool stuff. Anyway, one more video after this, and then we'll be ready for class. So stay tuned.